As we ran into in our second elimination problem, and as you may remember from solving systems in past years, sometimes we run into special cases when we are solving systems of equations. Cases where the systems may either have no solution or have an infinite number of solutions. So let's take a look at this system. We could go about solving it using either method. I will choose substitution. So if we want to use substitution, our first equation is easily solvable for x. Get that x is 3 plus 2y, which we can then substitute into our second equation, negative 2 times 3 plus 2y plus 4y equals 1. And then we distribute, which gets us a negative 6 minus 4y plus 4y equals 1. Now, negative 4y plus 4y is of course 0, those cancel out, so we're left with negative 6 equals 1. This is a false statement. Negative 6 is not equal to 1, and therefore this system has no solution. That is one of our special cases, the system that has no solution. And it happens in the case of linear systems when our two lines that these equations represent are parallel. There winds up being no solution. Another special case is where there are infinitely many solutions. If we have the system 2x minus y is equal to 1, and 4x minus 2y is equal to 2, I will choose to solve this one by elimination. If I multiply this first equation by negative 2, that gives me minus 4x plus 2x, plus 2y, sorry, equals negative 2. Now if we add them together, 4x minus 4x is 0, negative 2y plus 2y is 0, and 2 plus negative 2 is 0. 0 equals 0. That is a true statement, and therefore because 0 equals 0 is a true statement, that means we have infinitely many solutions. However, the relationship between x and y is still constrained by these equations. So, to show that relationship between x and y, rather than simply saying infinitely many solutions, we identify one of our variables. We say x equals a. We just pick an arbitrary letter, say x equals a, and then identify y in terms of x. So if x equals a, then 2a minus y equals 1 from our first equation, and therefore y equals 2a minus 1. So there are infinitely many solutions, but they all have the form a 2a minus 1. That is our second special case. Another situation that isn't exactly a special case, but also is a little bit different to deal with, is something like this. Positive 3. In a situation where you have fractions, you can go ahead and solve it just like we normally would by using elimination or substitution. However, it can be a lot easier to just get rid of the fractions. And to do that, we can multiply our first equation by the least common multiple of our denominators of 6 and 4. If we multiply our first equation by 24, then we won't have any more fractions to worry about. And that just makes it a little bit easier to solve. 24 times 1/4 is 6. 24 times 6, or 24 times 1/6 is 4. And 24 times 1 is, of course, 24. And from that point, we can solve the system just as we would any other system, using whichever method we prefer. In general, I prefer elimination. So I'm going to multiply this equation by 4 to cancel out y, which gives us 4x, 4y, and 3 times 4, which is 12, of course. Our y's cancel out. 4x plus 6x is 10x. 12 plus 24 is 36. So we get a result, x equals 36 over 10, which reduces to 18 over 5. Or you could also say 3.6, depending on whether you prefer fractions or decimals. Then we take this value, plug it back in to solve for y. The second equation is simpler, and it looks to me like using a decimal will be simpler. So 3.6 minus y equals 3. That gives us y equals 0.6. And so our solution then is the ordered pair 3.6, 0.6, or if we prefer fractions, that's 18/5, 3/5. You can similarly multiply to get rid of decimals if you wind up with an equation or a system of equations that has decimals in it. For example, if we have the equation 0.01 x plus 0.02 y equals 0.04, 0.01 x minus 0.02 y equals 0.01. Now you may notice this is set up for elimination right away if we wanted to go that route. But sometimes it is advantageous to get rid of our decimals. We can multiply both equations actually, by 100 and just move our decimal points over 2 spots. Therefore, changing our equations to x plus 2y equals 4 and x minus 2y equals 1. As I said, they're set up for elimination, so we can then add those two equations together. Noticing that green is difficult to see, so I'll switch out. 2y minus 2y is 0. X plus x is 2x. 4 plus 1 is 5. So x is 5 halves, or 2.5. And then we can plug that back in to find our value for y. 5 halves plus 2y equals 4. So we subtract 8 halves minus 5 halves, gets us 3 halves. So then dividing by 2, we get y is equal to 3/4. So our solution is the ordered pair 5 halves, 3/4. One final note about systems in general is that you can solve them on your calculator. Take this system, for example. if we were to rearrange our equations to solve for y, we would get y equals 0.04 minus 0.01 x over 0.02. And we could similarly rearrange our second equation, and if we punch those equations into our calculator, into the y1 and y2, you can then graph them and calculate the intersection using your calculator's graphing feature. So that is a good way, that is one way to solve systems. And even if I ask you to solve it using a different method, it is always a good way to check your result, which you can also do just by plugging your values back into the equation.